Okay, welcome again. So we're discussing sampling. When we had in the previous video, we had done some properties that we will be using in our forthcoming analysis. So as far as sampling was concerned, up to this point, we have expressed it in a way wherein the sample signal, say this xpt, it's obtained by multiplying the input signal x of t, which is the continuous time signal, with an periodic impulse train. So graphically it is something like this: x of t, p of t, we get x of p, but this is in time domain, fine. And we have also arrived at this expression that we can express sampling operation in time domain as this summation. Okay. Now we will go to the frequency domain analysis using these properties that we have discussed previously. Now in the time domain, xpt, which is your sample signal, is expressed as a multiplication of your continuous time signal with the impulse train, which means in the frequency domain, multiplication translates into convolution. So it will be something like this. Fine. This was the first property that we discussed like this. So same thing I have applied here. Now we have x of j omega. आपका कुछ continuous time signal होगा. It is its Fourier transform. Fine. So it can be graphically, let's assume कि let's assume that it is a typical signal. Okay, it's 90 volt. It is a typical signal frequency representation of x of t. So and let's take a typical value that it has a band of frequencies, something like this. Fine. So it is a band of frequencies, say from minus omega m to capital omega m. Fine. So this is x of j omega with respect to frequency. So it simply means you have a signal x of t. It occupies this band, this much of frequency. I mean, it has a frequency that ranges from minus omega m to capital omega m. Okay. Generally, when we go for sampling, we always band limit our signals in a practical scenario. So if you have a signal x of t and you want to sample it, so there's always a possibility that it may be contaminated by noise. So prior to sampling, we do a bit of filtering, right? Maybe you will study these things in the communication course. So filtering we make sure that x of t is band limited in the sense that the range of frequencies that are available in x of t, it's a well-defined range, it's a finite range. So here I am assuming I have band limited my signal x of t from minus omega m to capital omega m. Okay, so this will be a typical response of a signal that you encounter in the real world after filtering, after band limiting it. Fine. Then the second quantity is p of j omega. That is the Fourier transform of our impulse train. Fine. Now this we will analyze कि ये कैसा होगा. So we have defined our impulse train. Yeah, let's do one thing. Actually, यही से start करते. P of t, it was defined as summation n running from minus infinity to plus infinity delta t minus n capital T. Right? Now P of t is a periodic signal, so you can express it as Fourier series, and we can have a Fourier coefficient a of k calculated as 1 by t, say from minus t by 2 to t by 2, p of t e raised power minus j k omega naught t And yeah, this was t, and I think we had discussed ws, so we won't be using omega naught, we'll be using omega st. Fine. Now in this interval minus t by 2 to capital T by 2, if you see minus t by 2 will be somewhere here, so actually I should have expressed it in terms of t, 2t, 3t, and 4t, minus t, minus 2t. Now minus t by 2 is from here to t by 2 is here, and in this range, this is again one period t, we have the signal delta t. Right? So what I'm trying to say is that within these limits, we can substitute p of t by simply delta t. Fine. Okay. Then again, we know that if we have delta t multiplied by some signal x of t, it is actually equivalent to x0 delta t. अब delta t आपका ये है, x of t is this exponential signal. So if we go by this property, this will actually be 1 by t minus t by 2, t by 2. X of 0 is e raised power 0, which is 1. So it will be simply delta t dt. And we know that this integral is actually equivalent to 1, such that a of k will turn out to be 1 by t. Fine. Using this property. Now, p of t is a periodic signal. And if we take its Fourier transform, let's represent it by pj omega. Again, we'll be using this property, this one, Fourier transform of a periodic signal. You have a periodic signal x of t, you take its Fourier transform, it will be this summation. Fine. So if we apply this property here, my p of j omega, it will be summation k running from minus infinity to plus infinity 2 pi a subscript k delta omega minus k omega s. Fine. And a of k we just found out to be 1 by t. So if I make this substitution, my pj omega, it will be 2 pi by t bahar nikalte hain, because ak is 1 by t, and internally we will have summation k is equal to minus infinity to plus infinity delta omega minus k omega s, which means in the frequency domain जो आपका impulse train होगा, it will again be impulse delta omega minus k omega s separated by omega s and modulated, amplitude modulated by 2 pi by t. So if I try to express it graphically, let's go here, we'll see what will be its black here, so like this, and this is my central point. तो जो मेरा, okay, let's be consistent with the width, just a second. Okay, here to here, and then like this. So as per this expression, we will have impulses like this, and so on. Similarly on the negative axis. Fine. With some changes. Ab changes kya hogi? First change will be, so this is my p j omega with respect to omega. First change will be, these will be modulated. Now the amplitude will not be unity, it will be 2 pi by t. Fine. So this point right here is 2 pi by t. And second, they will be separated by omega s. So if this is 0, this will be omega s, 2 omega s, 3 omega s, 4 omega s, and so on. Similarly on the negative axis, something like this. and so on. So this will be the frequency representation of my impulse train. Fine. Okay, now that we have found pj omega, what remains is the last part, that how about this, what will this look like, xp j omega. Now we have already established it is 1 by 2 pi x of j omega convolved with p of j omega. Fine. In other words, if we expand it, it will be 1 upon 2 pi x j omega convolved with p of j omega. We have just found out to be 2 pi by t summation k runs from minus infinity to plus infinity delta omega minus k omega s. Fine. And you can make some adjustments. 2 pi and 2 pi will go, we'll have 1 by t, then within this summation we will have k is equal to minus infinity to plus infinity x of j omega convolved with delta omega minus k omega s. Now come to this property. If you are convolving a signal f of t with the shifted impulse, it is equivalent to this. So which means if I am convolving a signal x of j omega with the shifted impulse, it will be 1 by t summation तो वही रहेगा, and the result of this convolution will be x, that is this function shifted in frequency. Means it will be this signal x of j omega जो आपका original waveform था, shifted by omega s. In other words, if we try to plot it graphically in our existing plot, let me just have the axes here. So okay, we'll start from here to here. फिर हमारा ये like this. All right. Now let me just mark out the points. This is 0. Then I have omega s. And yeah, let's do one thing. Now as per this expression, जो मेरा xp j omega है, first it is modulated by 1 by t, that's fine. Then it will be replicating your x of j omega, जो उसका waveform है, जो उसका frequency behavior है, equally spaced by omega s. Okay, so effectively it will be something like this. Let's go here in red. So you will have these x of j omega, so something like this. Fine. Then there will be another one. So if I take this interval, like this, then another one like this. Similarly, I have from here this. Fine. So जो आपका ओरिजिनल वेव फॉर्म था x of t का जो frequency representation था, the band of frequencies, those bands of frequencies will be replicated. So this is my xp j omega. So those frequencies will be replicated like this. Fine. Now this is not actually matching with this. Actually it will be something like this 0 p, then this will be situated at omega s, because we are, as per the mathematical expression, you can easily find it out, it is k omega s, which means after every omega s, after every frequency interval of omega s, you will be replicating now what you call this input frequency band. ठीक है. अब यहाँ पे if we would have if we have used the same scale as this, so थोड़ा overlap हो जाता, but you should remember this is omega s. So this band from here to here, so it will be from minus omega m to capital omega m. This will be a result of multiplication of this with this impulse. Then this band from omega s, so this point here, it will be omega s minus omega m, fine. So, and this will be omega s plus omega m. This is multiplication of this band with this impulse. Okay. Similarly, this band, it will be located around 2 omega s. This will be minus omega s and minus 2 omega s. Right? Now, so we have observed that in time domain, it was simple multiplication, the waveform on the left side, fine. But when we did the analysis in the frequency domain, we found हमारा जो input है x of t, it will have some band of frequencies from minus omega m to omega m. फिर हमारा जो periodic impulse train है in the frequency domain, it will again be a train of impulse, fine. So in time domain, it was separated, the individual impulses, they were separated by a time period t. In the frequency domain, these impulses first, उनका amplitude is scaled by 2 pi by t, and they are separated in frequency by an amount omega s. Now omega s is the sampling frequency. And finally जो हमारा sampled signal है xpt in the time domain में तो simple है, जहाँ जहाँ पे आपका impulse और signal match हो रहा है, you will have a waveform wherein these individual impulses, they are modulated in amplitude by the amplitude of x of t. But in frequency domain, it turns out whatever mathematical analysis we have done is that the result of this multiplication in time domain is actually equivalent to convolution in the frequency domain, which means graphically wherever this impulse appears, around that impulse जो आपका original signal है in the time domain, it is built. As you can see, this convolve with this every time, at every frequency instant जहाँ पे आपका impulse है, उसके around आपका जो input waveform है, it gets replicated. Like here, it is surrounded around 0. This one is surrounded around omega minus omega s. This one is built around minus 2 omega s, and so on. Similarly, on the positive axis, this waveform around omega s, this waveform around 2 omega s, and so on. Right? Now, the important thing here is these points. Now deliberately मैंने ये waveform ऐसे बनाया है wherein I have kept a space between these waveforms, between these subsequent waveforms. This is an ideal case. This is what we want. अगर आपका sampling ऐसे हो रहा है wherein you have chosen WS, that is sampling frequency, in such a way that after you have done the sampling process, जो आपका sampled version है in the frequency domain, if it is waveform is something like this, it is okay. You can reconstruct your waveform. In other words, I am putting a limit here. अगर आप waveform observe करेंगे, here I have omega m, this point is less than omega s minus omega m, because there's a spacing between these two waveforms, fine. So in an ideal case, yeah, आप कह सकते हैं कि when there is sampling is done in such a way कि जो आपके individual bands हैं, they are not overlapping, fine. So for this is an important point here, this will give us a sampling theorem. So for no overlap between the shifted replicas of xj omega, we have to make sure that this point omega m should be less than omega s minus omega m. Okay? Then if you do a bit of shifting, omega m plus omega m less than omega s, which means omega s should be greater than twice omega m. And this is basically your sampling theorem. fine, which states that if your sampling frequency omega s is greater than या equivalent to omega m, then only जो आपका वेव फॉर्म है, ओरिजिनल वेव फॉर्म, is faithfully reproduced. Physically, it means if you ensure this thing, you are doing the sampling process and you know आपका signal x of t है, you know it is band limited, you know what the value of omega m is. Omega m is basically the maximum frequency that is available in your input signal. And if you ensure कि आपका जो sampling frequency है, it is at least twice the maximum frequency available in your input signal, then only you can do a faithful sampling, in the sense that once you are done with the sampling, आप वापस reconstruct कर सकते हैं अपना original waveform from the sample version. Fine. Now, if this is not met, अगर आपका omega s is less than twice omega m, now graphically that would mean कि आपका ये वाला point है, it will be here. So let me draw it separately. तो उस time पे it will mean कि आपका जो waveform है, it is something like this. ये आपका पहला रेप्लिका आ गया, situated around omega s, around 0. This is minus omega m plus omega m. और आपका जो दूसरा वेव फॉर्म है, it is kind of overlapping. Now this is the overlapping part. और अगर ऐसा हो गया, you can see there is overlapping. आपके जो individual replicas है x और j omega के, they are not distinguishable, there is overlapping. And under such circumstances, you cannot recover x of t faithfully exactly from xp of t, and this condition is known as aliasing. Fine. It is a spilling of energy, I can say. There is an overlap between these reproduced what you call frequency bands, या जो आपके replicas है, and this happens जब आपका sampling frequency is less than twice the maximum frequency that is available in the original signal x of t, and this process is known as aliasing. So for faithful sampling, this was the purpose of this what you call and this entire analysis. It was just to show you that there is basically a what you call a limit कि आप किस हद तक sampling कर सकते हैं. And this was a typical analysis that kind of is actually a proof for the sampling theorem. We have done the analysis in time domain, and side by side I have shown you what happens in the frequency domain using appropriate laws, using appropriate properties of their transform. And for faithful representation, this is our typical case. This is what we want from sampling. कि हमारा sampling ऐसा होना चाहिए, it should be done at a certain frequency such that जो individual bands है आपके sample signal में, they should be identifiable, they should be separate, they should be isolated from each other. And if this you are able to achieve this, आपका sampling faithfully हो जाएगा, then you can, आप आगे देखेंगे, we pass this signal through a filter which is tuned to this particular band, and you'll get your original band back. But if there is spilling, if there is overlap, फिर जब आप इसको filter के through pass करेंगे, you won't be able to get this entirely, which means आपका जो sampling है, it has failed. Right? So that's why sampling is governed by this sampling theorem, wherein we have to ensure that sampling frequency, at least it should be equivalent to twice the maximum frequency component that is available in your input. Okay? So this was slightly way beyond the scope of this course. आपका जो sampling का actual था, in the second chapter, it was just a time domain analysis, just a brief introduction. But since this is a core process, you will be using this a lot, especially in communications and later on in digital signal processing. So I thought we should give it a full go. We should have an in-depth analysis of this sampling process. Fine. So that's it. This completes your first 3 chapters, and next videos, they will be related to the Laplace transform. This will again be the frequency domain analysis. Like I said, for continuous time, we have Fourier analysis and Laplace. And for discrete time, we again have Fourier analysis, and then we have the Z transform. So next, we will be doing the Laplace transform.